In this case study, we're going to try and work out the electric field caused by a charged ring. So we have this red ring over here, which has a charge Q uniformly applied to it, radius r. And we're trying to work out what the electric field it produces is at some point. To make things easier, we'll pick that point to be along the axis, somewhere along the z-axis as it's shown here. That means it's simple enough we can solve using calculus. The numerical method we will show you will allow you to solve it anywhere, but the calculus method can only handle along the axis somewhere. Okay, so how do we do this? First step, of course, is to think of the physics. So if we've got positive charges all the way around here, uniformly distributed around the ring, they're going to apply an electric field that moves away from them. And the way to work out the electric field at some particular point is just, as usual, adding it up. So for example, at this point here, there's going to be an electric field caused by that charge over there, which is going to point in this direction. There's also going to be an electric field from this charge down there, which is going to point in that direction, and similarly from all the other points on the edge. And that will probably add up to give a net charge going along the axis. If you're on the other side, over here somewhere, it's probably going to give you a net electric field that goes that way. If you're in the middle, you're going to be pushed down by the charges at the top, up by the charges at the bottom, and it'll probably cancel out to 0. So we can think of limiting cases. If we plot Z versus the strength of the electric field, then right at the middle it's going to be 0 because the charges are all around you and so will cancel out. As you get further out, it'll get stronger. It's going to go up, and it's going to go down as you go the other side. When you're really far away, so zooming out, let's imagine the loop is now looks like this and you're right over here, you could just treat the loop as a point charge. So it's going to obey the normal inverse square law. So at large distances it's going to behave like the inverse square law, so it's probably going to join up something like this. So any solution that doesn't look like that is probably wrong. Okay, so how do we calculate it? Well, we're going to need to divide up this ring into little bits. Simplest way to do it is with angle. So let's say pick an angle here, theta, and have a delta theta in there. Then we can treat this little bit of the arc along here as our point charge and work out what its electric field is here. And then we can sum over all the thetas, going from 0 to 360 degrees, to work out the total field. So let's try and work out the step for that. The location here, if it's angle theta from x, it's going to be, x coordinates are going to be r cos theta. Y coordinates going to be r sine theta, and 0 in the z direction. Okay, so this vector from the charge there to where we're going to measure it is the displacement vector. So r is going to be this point here, which is got coordinates 0, 0, let's call it z0. So r is going to be the vector from here to here, which is this minus that. So it's going to be minus r cos theta minus r sine theta and z0. Now what's the electric field? Well, we know we're going to treat this little bit as a point charge. What's the charge of that little point charge here? We can call it delta Q. Now delta Q is going to be a small fraction of the total charge, and we can work out what that fraction is by taking the ratio of lengths. So delta Q over the total charge has got to equal delta theta over the total angle, which is 2 pi in radians. So if delta theta is 1% of the total angle, it's going to have 1% of the charge. So it's pretty straightforward. So delta Q, the Q charge of that little segment over here, is just going to be Q over 2 pi delta theta. Theta, the little angle in here. Okay, so we now know the charge. We know from Coulomb's law that the electric field is going to be 1 over 4 pi epsilon naught times the charge, which is Q over 2 pi delta theta, times R over mod R cubed. Remember, the normal form of the equation has got 1 over mod R squared and then the unit vector here. But if we replace the unit vector with the actual vector, we need to have an R cubed to compensate, just like we did last time. So we know what R is. We know what everything is except mod R. So if R is this, mod R is going to be the square root of this squared plus this squared plus this squared. So it's going to be R squared cos squared theta plus R squared sine squared theta plus Z naught squared. Now if you remember from your trigonometry, cos squared plus sine squared equals 1, so that's just going to be equal to R squared plus Z naught squared. So we know that our electric field from that little segment, so that's the, I should probably call it a delta electric field because it's only a little bit of the total electric field, it's going to be 1 over 4 pi epsilon naught Q over 2 pi delta theta R, which is minus R cos theta minus R sine theta Z naught all over R squared plus Z naught squared to the 3 halves. So that's the square root, which is the half power, cubed. So that's our step function, step equation.